We now move on to topic 4, which is covering periodic trends, or in other words, trends of the periodic table. Before we get started, we're going to go ahead and start with section 1, which is going to talk briefly about the history of the periodic table and review how it's laid out. So on this slide right here, it just provides a brief glimpse into some of the major discoveries of the periodic table and who the scientists were behind those discoveries. So we start off with John Newlands, and John Newlands was arranging elements by increasing atomic mass. His big contribution was that he noticed that there was the repetition of properties for every eighth element. This was known as the law of octaves. The idea was that you could predict properties of elements based on that pattern. The next scientist to make a contribution to the periodic table is Lothar Meyer. Lothar Meyer demonstrated a connection between atomic mass and elemental properties, much like John Newlands did. He arranged the elements in order of increasing atomic mass as well. The two big names, though, that I need you to know for the history of the periodic table are Dimitri Mendeleev and Henry Mosley. Dimitri Mendeleev demonstrated a connection between atomic mass and elemental properties as well. But what he did is he started to arrange the elements by increasing atomic mass, much like he would take index cards and write the element of that write an element on that index card and lay them out. Doing so left blanks or spaces in his chart, and he predicted the properties of elements that haven't even been discovered at that point. Dimitri Mendeleev is credited for creating the first organized periodic table. Now, that was a great step in the right direction, but the problem was that arranging elements by increasing atomic mass wasn't necessarily the most accurate. In fact, when we started to discover the subatomic particles, particularly discovering the proton, we discovered that that was a better way. And so Henry Mosley is credited for putting together our modern periodic table. He discovered that atoms contain a unique number of protons, which he would then call the atomic number. And so the elements were arranged in his periodic table based not on atomic mass, but instead by atomic number. This is a very short history of the periodic table. We don't need to go much more than that. But that does give us an idea of where we've come from and who the major contributors were. As a reminder, you will need to know the groups of the periodic table if you don't know them already. And so as a reminder, the main group elements, which are considered to be the higher columns in the periodic table, groups 1, 2, and then 13 through 17, that's their general title, are the main group elements. They could further be classified into some specific groups. For example, the alkali metals are group 1, alkaline earth metals are group 2, and halogens are group 17. Also included in the main group elements, which is located on this slide, are the noble gases, which are group 18. And then the elements that fall down in groups 3 through 12, those are considered to be the transition metals. Let's not forget those two rows at the very bottom of the periodic table, which are sometimes referred to as the inner transition metals, but we also refer to them as the lanthanides and the actinides. Now, we've discovered that elements that exist in the same group tend to have very similar chemical properties. And the reason for this is because they contain the same number of valence electrons, which we learned in the last topic are the electrons involved in chemical bonding. So now that we have a general understanding of the periodic table, let's talk about effective nuclear charge. If you take anything out of this topic, it should be effective nuclear charge. Because if you can understand effective nuclear charge and also the shielding effect, which is what we'll talk about as well, then you will be able to explain the periodic trends that we cover in this video. So with that being said, let's talk about what effective nuclear charge is. First of all, let's just simply start off with what nuclear charge is. When you hear the word nuclear, what comes to mind? You might think of the word nucleus. And remember, what's in the nucleus? The nucleus is composed of two subatomic particles, protons and neutrons. Now, when we talk about nuclear charge, or in other words, the charge of the nucleus, what subatomic particle is responsible for that? Considering neutrons don't have a charge, it must be then the protons. So protons are what is contributing to the charge of the nucleus. And therefore, when we say nuclear charge, we're simply referring to the protons. And so notice, what's the symbol for nuclear charge? It's the letter Z. And if you remember back to topic 2, when we were doing isotope notation, the bottom number of that isotope notation was also the letter Z. And remember what that stood for? That was the atomic number, or number of protons. So nuclear charge is just simply the number of protons that an atom has. Now, the number of protons are located inside the nucleus, and so all that positive charge is located at the center of the atom. Then we learned in topic 3 that the electrons, which are negatively charged, surround the nucleus in these fixed orbits. And so we have a very simplified view of the atom just to show a point. You see you have electrons in this first shell, and then you have these electrons in this outer shell. These outer electrons are referred to as the valence electrons. Now here's the thing. These outer electrons are experiencing a double phenomenon. On the one hand, they're feeling attracted to the positive nucleus. But on the other hand, they're feeling repelled by the electrons that are inside the lower shells. So the electrons on the outside of the atom are being what we call shielded. They aren't feeling the full positive effect of the nucleus. Instead, they're feeling what we refer to as the effective nuclear charge, which has the symbol Z sub F. And what this is defined as it's defined as the actual magnitude of positive charge experienced by an electron. In other words, these outer electrons don't feel the full nuclear charge. They feel the effective nuclear charge, which is something lower. For example, if this was neon would have 10 protons. Do you think these outer electrons actually feel the full effect of those 10 protons? No, they're going to feel something less than that. They're going to feel what we call the effective nuclear charge. Now, we don't need to worry about what that value is. We just need to know that it's lower because of the shielding of these inner electrons. And so the shielding effect is that simultaneous phenomenon we talked about, in which those outer electrons are both attracted to the positive nucleus, but then also repelled by the inner electrons. So the effective nuclear charge and shielding effect are going to be what guide us through this topic. If we talk about the trend, if we look at the periodic table and want to look at the pattern and trend of effective nuclear charge, we would notice that an effective nuclear charge increases as you move from left to right. But why is that? Well, let's consider two elements. Let's look at lithium compared to neon. They're in the same period, but one's on the left side, one's on the right side. Lithium has 3 protons. Neon, on the right side, has 10 protons. Now, what do these two elements have in common? Because they're both in row 2, they both have 2 energy levels, n equals 1 and n equals 2. So in both of these, I'm getting a little tight there, in both of these examples, these atoms have valence electrons in the second energy level. And I'm just drawing just general amounts of electrons, not necessarily accurate. All right. Effective nuclear charge is defined as the magnitude of charge that the outermost electrons feel. Which valence electrons or outermost electrons do you think are going to feel the most from the nucleus? These outer electrons in energy level 2 being pulled by 3 protons, or these outer electrons in energy level 2 being pulled by 10 protons? Because neon has more protons in the nucleus, yet the same number of shells, these outer electrons would experience a higher effective nuclear charge. And that's why it increases as we go from left to right. Now, let's contrast lithium to the element right below it, which is sodium. Sodium has 11 protons, a lot more than 3. But sodium's outermost or valence electrons are actually in the 3rd energy level. So on the one hand, sodium has a higher or stronger nucleus than lithium does. But on the other hand, its outer electrons are further away. So does that mean sodium has a higher effective nuclear charge or a lower effective nuclear charge? It's kind of hard to tell, isn't it? And that is why the group trend, as we go down, is excluded. It's hard to tell. And so we're only going to focus on the period trend when it comes to effective nuclear charge. So let's take a look at example 1 and make sure we understand the trend. Take a look at the 4 elements listed. We have aluminum, sodium, argon, and phosphorus. Question is, rank those following elements in order of increasing effective nuclear charge. So, I'm going to have my 3 greater signs so I can place the 4 elements in the appropriate spots. The highest effective nuclear charge on the right, and the lowest effective nuclear charge on the left. If I take a look at where these 4 elements are on the periodic table, I notice that they are all 4 in row 3. So if I take a look at row 3, I know that effective nuclear charge increases as I move to the right. And so, which element of those 4 is all the way to the right? And it looks like argon is the furthest to the right. The next element below that would be phosphorus, followed by aluminum, and finally sodium would have the lowest. This concludes sections 1 and 2. We'll see you in section 3.